Hello again, and welcome back to video 2 of Module 7. My name is Kara Tobin, and during this video, we are going to be looking at sanitation emissions. In particular, we will be looking at opportunities for value creation while reducing sanitation-related emissions. We will want to answer, what are the biggest emission sources, and how can we improve sanitation processes to reduce emissions while creating value? According to the World Economic Forum, water and wastewater utilities account for 5% of global greenhouse gas emissions, much of that being energy. 70% of these emissions come from wastewater treatment, such as from sludge treatment facilities. Here you see one in Gansbaai, South Africa. The most prominent greenhouse gases from sanitation are methane, or CH4, and carbon dioxide. Methane is generated through the anaerobic digestion of organic matter in wastewater treatment plants and landfills. Carbon dioxide is produced from the combustion of fossil fuels used to operate wastewater treatment facilities. Nitrous oxide, or N2O, is also produced during wastewater treatment, but it has a smaller contribution. Nitrous oxide can be generated through processes such as nitrification, for example. In many African countries, nitrous oxide is emitted from uncollected and untreated human waste where populations are not connected with a sewer system. Emissions from wastewater treatment are growing rapidly. As we close the gap on sanitation using conventional methods, it will mean an estimated increase in 10% of greenhouse gas emissions by the sanitation sector. Here we see one of the famous wastewater treatment plants in Santiago, Chile, where an increase in domestic wastewater is causing the need to treat more wastewater and sludge. According to the Nature article provided in your pre-reading, in Chile, wastewater treatment is projected to produce 50% or half of national emissions in Chile by 2027. If you live in Africa, particularly in the rural regions, you have most certainly seen simple pit latrines. Globally, according to a WHO-UNICEF study in 2021, an estimated 1.6 billion people use pit latrines, predominantly in sub-Saharan Africa. But are you aware that pit latrines contribute to 1% of African methane emissions? Wastewater has been identified as one of the key contributors to anthropogenic, or human-caused, methane-based emissions. The severe danger is that methane has a high global warming potential and is relatively short-lived compared to CO2, or carbon dioxide. I have a little-known science fact for you. 1 ton of methane can be considered to be equivalent to approximately 35 tons of carbon dioxide when looking at its impact over 100 years. Thus, cutting methane emissions has more immediate benefits than other greenhouse gas savings. This is great news in how curbing sanitation emissions can make a huge impact. In Module 3, you have already seen how the circular economy can extract value from sanitation resources. Here, I will highlight how sanitation waste streams can be used to reduce emissions. According to the Nature article provided in your pre-reading, the degradation of organics during wastewater accounts for approximately 5% of non-carbon dioxide greenhouse gases. Fun fact: if we can capture those organics, they can become valuable waste streams. For instance, using biogas can reduce greenhouse gases by 1.5 tons of carbon dioxide equivalent per household. Upcycling of sanitation organics can also help us address the agriculture industry, which is the biggest source of human-caused methane emissions. Recycling wastewater products for fertilizer can reduce emissions and country energy use. For example, substituting 5% of existing nitrogen fertilizer from human excreta could save more than 1.5% of China's annual electricity production. Now I will show 2 examples of reusing or upcycling wastewater in Africa. This first image is in Durban, South Africa. Here, wastewater is reused for industrial purposes. The highly treated wastewater, otherwise known as new water, can be used to meet growing demands for industries and for cooling. The Durban plant was developed by Veolia Water Technologies to switch manufacturing processes to recycled water. 98% of the wastewater is recycled, freeing up 47,000 cubic meters a day of water which can be used for consumption. Meanwhile, wastewater from the Boukalef treatment plant in Morocco is used for watering golf courses and municipal green spaces in Tangier. This is increasing water quantity and reducing stress on very scarce freshwater resources. Rather than pumping and conveying scarce and often uneasily accessible fresh water, many African sites are tapping into the reusable potential of wastewater, such as this one in Morocco. It has been estimated that if wastewater is properly treated for reuse, it can be applied to over 42 million hectares for irrigation. That is a lot of farmland that can be used to feed many people. This video showed the major emission sources from wastewater treatment, namely methane, carbon dioxide, and nitrous oxide. 2 key takeaways on emissions include: methane release is a growing problem globally due to its long lifetime. Wastewater emissions are growing rapidly and may become a major source of emissions in your country. So how again can we reduce emissions while capturing the value of wastewater resources? Organics can be reused for fertilizers and biogas can be captured for energy. Both examples of upcycling can lead to significant energy reductions globally. Already some African countries are reusing water for cooling and irrigation. Reuse of new water has the potential to save thousands of cubic meters of water per day in urban areas. Perhaps you can think of where water can be used in your city. Now I will leave it to you to test your newfound knowledge. There will be a quiz after this video. I look forward to seeing you for video 3 of Module 7. Bye for now.